What if what you see in the sky isn't real? This audiobook invites you to explore one of the most astonishing phenomena in the universe: gravitational lenses. Gravity can warp space and bend light, creating cosmic mirages where a galaxy multiplies, distorts, or appears amplified as if by magic. But it's not magic, it's pure physics. Discover how these visual deceptions reveal hidden secrets of the cosmos and even clues about the mysterious dark matter that envelops everything. If you've ever looked through a distorted glass and seen how the image of what's behind it changes, you have a basic idea of how these cosmic mirages work. Just like that glass, massive objects in the universe act as lenses, distorting and amplifying the light coming from more distant objects. But how does this relate to the theory of relativity? Einstein proposed that gravity is not just a force that attracts objects, but it can also curve the very fabric of space and time. When this curvature occurs, the paths of light are altered, creating stunning visual effects. Imagine the universe as a giant spider web. Each thread of the web represents a light path. When a massive object, like a galaxy, is placed in the path of that light, a distortion occurs that changes the direction in which it travels. Thus, instead of reaching our eyes directly, the light curves, allowing us to see the object through a cosmic mirror. Isn't it amazing to think that we can see objects that are billions of light years away thanks to this curvature? This phenomenon is not just a visual spectacle, it has profound implications in cosmology. Astronomers can use gravitational lenses to study the distribution of dark matter in the universe. Did you know that although we cannot see dark matter, we can infer its existence through its gravitational influence? Gravitational lenses allow us to see what would otherwise be invisible, adding a completely new dimension to our understanding of the cosmos. Cosmic mirages also raise intriguing questions about the nature of the universe. For example, what do they tell us about its structure and evolution? By observing how the light from the most distant galaxies is distorted, scientists can gain insights into the distribution of matter in the universe and its expansion. In other words, these mirages are not only beautiful, they are crucial tools for unraveling the mysteries of the cosmos. As we delve into the study of gravitational lenses, it's important to ask, what was the path that led scientists to discover these phenomena? From Einstein's early theories to modern observations with powerful telescopes, the history of gravitational lenses is a story of curiosity and discovery. Each advancement brings us one step closer to understanding how the universe works. And each new revelation raises even more questions. On the other hand, it's fascinating to think about how general relativity, proposed over a century ago, remains relevant today. How is it possible that a theory developed in the 20th century can have such contemporary applications? The answer lies in the very nature of science. We are always building on what has been previously discovered. Relativity not only revolutionized physics, it also opened the door to a new approach in cosmology. And what about the practical applications of these theories in our everyday lives? Although it may seem that cosmic mirages are distant and abstract phenomena, their study has led to developments in technology and methodologies that affect multiple disciplines. From GPS navigation to medical research, concepts derived from general relativity have a tangible impact on our world. So the next time you look up at the night sky, remember that there is more than meets the eye. Behind every star and every galaxy, there is a story to tell, a story involving light, gravity, and the curvature of space-time. Cosmic mirages are a window into that story, a reminder that the universe is a place full of wonders and mysteries that we are still trying to unravel. In summary, cosmic mirages are much more than mere optical illusions. They are tangible evidence of the theory of relativity and valuable tools in cosmological research. They invite us to observe the universe with new eyes, to question what we know, and to explore the unknown. With each discovery, we get a little closer to understanding our place in the vast and enigmatic cosmos. So get ready for an exciting journey through the mirages of the universe, where science and wonder intertwine in unimaginable ways. The story of gravitational lensing is a fascinating journey through time and space. It all began with a man whose name has become synonymous with genius, Albert Einstein. In 1915, Einstein presented his theory of general relativity, which revolutionized our understanding of gravity. But how did a simple idea transform into the notion that light can be bent by gravity? Imagine a trampoline with a heavy ball in the center. This ball creates a depression in the surface, and if you roll a marble near it, the marble will follow a curved path around the ball. This is how Einstein visualized gravity, not as a force that pulls objects, but as a curvature of space-time. This concept is fundamental to understanding how massive objects, like galaxies, can act as lenses that distort the light from more distant objects. The first glimpse of the concept of gravitational lensing appeared when Einstein wondered if the light from stars could be influenced by gravity. In 1920, an astronomer named Arthur Eddington conducted an experiment during a solar eclipse to verify this idea. Eddington observed that the light from distant stars was bent as it passed near the sun, thus confirming Einstein's theory. This moment marked the beginning of a new chapter in cosmology, where curiosity and science began to intertwine in unexpected ways. But the story doesn't end there. Throughout the 20th century, scientists began to explore the implications of general relativity more deeply. As more powerful telescopes were developed, fascinating discoveries were made. In 1956, a group of astronomers observed a distorted image of a distant galaxy, a phenomenon that would become a milestone in the history of astronomy. This galaxy had become a kind of cosmic mirror, and the term gravitational lens began to gain popularity. Over time, gravitational lenses became a key tool for astronomers. They allow the study of objects that would otherwise be invisible, such as the oldest galaxies and dark matter. But what about the different types of gravitational lenses? As researchers delved deeper into the study, they realized that there were strong, weak, and micro lenses. Each of these categories has unique characteristics that help astronomers unravel the secrets of the universe. Strong gravitational lenses are the most striking and dramatic. When a massive object, like a galaxy cluster, perfectly aligns with a distant galaxy, arcs and rings of light can be observed floating in space. These visual phenomena are true cosmic mirages, and their study has provided invaluable information about the structure of the universe. Weak lenses, on the other hand, are less dramatic but equally important. They do not produce such clear images, but their cumulative effect can reveal the distribution of dark matter on large scales. Microlenses, although more subtle, can help detect exoplanets and other hidden features in the cosmos. Each type of lens offers a new perspective on the universe, and each discovery is a step closer to understanding our place in it. As we progress through this story, it is important to recognize the role that technology has played in the development of the concept of gravitational lenses. Modern telescopes, such as Hubble and more recently the James Webb Space Telescope, have allowed scientists to observe phenomena that were previously unimaginable. The ability to capture the light from stars and galaxies billions of light years away has opened a window to the universe's past. Interest in gravitational lenses has grown exponentially in recent decades. Astronomers are not only seeking to understand how they work, but they are also using these tools to investigate deeper questions about the nature of dark matter and dark energy. These mysteries are fundamental to our understanding of the universe, and gravitational lenses are a key piece of the puzzle. The story of gravitational lenses is ultimately a testament to human ingenuity and the desire to know the unknown. From Eddington's early experiments to current observations, each discovery has been a step forward in our quest to understand the cosmos. But the question remains, what else will these fascinating lenses reveal to us in the future? So as we contemplate the vastness of the universe, let us remember that gravitational lenses are not just a physical phenomenon, but also a symbol of human curiosity. Every distorted flash of light we observe is a reminder that there is still much to discover. The story of gravitational lenses is, at its core, a story of exploration, and the journey has only just begun. Einstein's general relativity is one of the most fascinating and revolutionary theories in modern physics. What if I told you that gravity is not simply a force that attracts objects, but rather a distortion of space and time itself? This may sound a bit strange, but this is the fundamental premise that Einstein presented in 1915. The idea that massive objects like planets and stars can curve the space-time around them completely transforms our understanding of how the universe works. Consider a trampoline. If you place a bowling ball in the center, you'll notice that the trampoline dips in that area. Now, if you roll a marble near the bowling ball, the marble will start to orbit around the ball, drawn in by the curvature of the trampoline. In this example, the bowling ball represents a massive object like the sun, and the marble symbolizes a planet like Earth. This is how gravity works in the view of relativity. It is not a force acting at a distance, but a manifestation of the curvature of space-time. Now, an intriguing question arises: how does this idea relate to light? It's easy to think that light travels in a straight line, but in reality, light is also affected by the curvature of space. So when light from a distant star passes near a massive object, like a galaxy, its path bends. This phenomenon is what we know as gravitational lensing. Light becomes a traveler that deviates from its original path, creating stunning visual effects. General relativity not only helps us understand gravity, but it also offers us a new way of seeing the cosmos. Imagine you are in a vast ocean of stars. Each star, each galaxy is like a floating buoy. Some are larger and heavier, while others are smaller and lighter. The large buoys, representing massive objects, create waves in this ocean. These waves are the curvature of space-time, and the small buoys are the lighter objects that in turn are influenced by those waves. But why is this understanding of gravity important? General relativity has allowed scientists to make predictions about phenomena that were previously completely mysterious. For example, gravitational waves, which are disturbances in space-time caused by extremely energetic events, were first detected in 2015. This was a monumental confirmation of Einstein's ideas and an open door to new explorations in astrophysics. As we delve into the world of gravitational lenses, it is important to remember that this is not just a theory. It is a tool that astronomers use to unravel the secrets of the universe. But how does this lens work exactly? When a massive object lies between us and a more distant object, it acts like a cosmic magnifying glass, amplifying and distorting the light from the distant object. This allows us to see things that would otherwise be hidden from our view. General relativity also faces a big question. What happens when we talk about extreme situations, like black holes? In these contexts, the curvature of space-time becomes so intense that even light cannot escape. This leads us to consider the deeper implications of relativity. Time and space are not fixed entities, but can be shaped and distorted by what exists in the universe. Imagine you are on a journey approaching a black hole. As you get closer, time starts to behave strangely. To someone at a distance, it seems like your clock is slowing down. This is another of the wonders of general relativity, which shows us that time is relative and can change depending on the gravity you are exposed to. One of the most exciting ideas that arises from general relativity is the notion that the universe is dynamic and constantly changing. Just as the surface of a lake can be disturbed by a stone thrown into it, the fabric of space-time can be altered by massive objects moving through it. This means that every star, every galaxy is contributing to the way we experience the universe. Finally, general relativity is not just a theory for understanding gravity. It is a bridge to a deeper understanding of the structure of the cosmos. It invites us to question what we think we know and to explore the unknown. This journey takes us to a reality where gravity is not just a force, but a complex dance between space, time, and matter. Thus, Einstein's general relativity not only changed our view of gravity, but also opened our eyes to a universe full of possibilities. Every discovery we make in this field brings us a little closer to unraveling the mysteries that surround us, and every question that arises pushes us to keep exploring what lies beyond what we can see. In this vast cosmos, the journey never ends. When we talk about gravitational lenses, it is fascinating to imagine how the universe plays hide and seek with light. Have you ever wondered how a massive object can become a type of lens that distorts the light from what is behind it? This phenomenon is the result of gravity, but not the gravity we are used to seeing on Earth. It is a gravity that has the power to curve space and time, something that Albert Einstein taught us through his revolutionary theory of relativity. The essence of a gravitational lens lies in the ability of a massive object, such as a galaxy or a cluster of galaxies, to affect the path of light passing nearby. Imagine you're observing a lamp from a considerable distance, and suddenly a large object comes between you and the light it emits. What would happen? The light from the lamp would be altered. It might appear to curve or even create multiple images of the same lamp. In the cosmos, this effect is impressively intensified due to the immense distances and masses involved. When a massive object acts as a lens, what happens is that the light coming from more distant objects is distorted and amplified. Can you imagine seeing a bright arc in the sky that is in fact an object that is billions of light years away? This occurs because the gravity of the massive object is curving the space around it, creating an optical effect that allows us to see beyond what we normally could. The concept of gravitational lensing leads us to question the structure of the universe. How can such distant objects influence our perception? The answer lies in the fact that light travels through a universe that is not flat but is filled with bumps and undulations, thanks to the gravity of the masses present. Thus, gravitational lenses become powerful tools for astronomers, allowing them to study not only what is in front of the lens, but also what is behind it. And gravitational lens types can be classified into several categories. Imagine you have a telescope in your hands. When you look through it, you can observe different celestial objects. Similarly, gravitational lenses can be strong, weak, or even microlenses. Strong lenses create spectacular images, while weak lenses produce subtle distortions that require careful analysis to detect. Microlenses, on the other hand, are like small magnifying glasses that can reveal hidden details of distant stars or planets. One of the wonders of this phenomenon is how these visual effects manifest. Have you ever seen a bright ring in the sky? This ring is known as the Einstein ring, and it forms when the light from a distant object perfectly curves around a massive object. It's as if the universe is creating art with light, and we, as spectators, are lucky enough to be part of this cosmic spectacle. Gravitational lenses are not only fascinating for their visual beauty, but they also offer us clues about the composition of the universe. What about dark matter? This is one of the most intriguing questions facing astronomers. Dark matter does not emit light and is difficult to detect, but its presence can be inferred through the effects of gravitational lenses. By studying how galaxies act as lenses, scientists can gain valuable information about the distribution and amount of dark matter in the universe. The observation of gravitational lenses has become a discipline in itself, utilizing advanced tools and techniques. Modern telescopes can capture even the subtlest distortions in light. As technology advances, astronomers are discovering more and more about how these lenses work and what secrets of the universe they can reveal. Isn't it impressive to think that with a simple change in the direction of light, we can open a window into the past of the cosmos? As we continue to explore these wonders of the universe, it is essential to remember that gravitational lenses are more than just astronomical curiosities. They are a bridge that connects us with fundamental questions about the universe. How did galaxies form? What is dark matter? How is the universe expanding? Each answer leads us to new questions, creating an endless cycle of discovery. With each lens we study, we unravel a little more of the mystery of the cosmos. Human curiosity, that innate drive to understand our place in the universe, is fueled by these phenomena. And so when we look at the stars, we do not just see twinkling lights, but also the footprints of gravity in action, shaping our perception of the infinite. In summary, gravitational lenses are more than a visual phenomenon. They are a key to understanding the universe as a whole. They show us that the cosmos is a dynamic and fascinating place where light and gravity dance in a cosmic symphony. So the next time you look at the sky, remember that each star, each galaxy could be telling you a story through its light, and that gravitational lenses are a mirror reflecting the secrets of the universe. Gravitational lenses are a fascinating phenomenon that shows us how the universe plays with light. But did you know that not all gravitational lenses are the same? There are different types that play various roles in the cosmos. In this section, we will discover together the three main categories of gravitational lenses: strong lenses, weak lenses, and micro lenses. How does each of them work, and what secrets of the universe do they reveal? Let's start with strong gravitational lenses. Imagine you are in a place where the light from a distant star passes near a massive object, like a galaxy. The gravity of that galaxy acts like a kind of cosmic magnifying glass, distorting the light from the star and creating duplicated images or even bright rings. This effect is known as the Einstein ring. Can you imagine seeing a ring of light forming around a distant galaxy? It's as if the universe is using a magic trick to show us what lies beyond what we could normally see. Now let's move on to weak gravitational lenses. Although the effect of these lenses is less dramatic than that of strong lenses, they are equally intriguing. In this case, the light from a distant galaxy is slightly curved as it passes near a galaxy cluster that acts as a lens. But how do we know this is happening? Astronomers can detect this subtle effect by observing the shape of distant galaxies. When light is curved, galaxies may appear more elongated or distorted. This phenomenon is like looking through a slightly curved glass and seeing altered images. Although it is not as spectacular as a bright ring, weak lenses are crucial for understanding the distribution of dark matter in the universe. Finally, we have micro lenses. These are the most subtle of the three and are often overlooked. In this case, smaller objects like individual stars or planets can act as lenses. When the light from a distant star passes near one of these objects, it can temporarily increase in brightness. This effect is like using a magnifying glass to focus sunlight on a specific point. You can see how something that wasn't so bright becomes a flash. Microlenses are especially interesting because they allow us to detect planets that are far from our galaxy, expanding our possibilities of finding Earth-like worlds. So why is it important to understand these different types of gravitational lenses? Each of them offers us a unique window into the cosmos. Strong lenses reveal the architecture of galaxies and give us clues about their mass. Weak lenses are like maps that help us understand the distribution of dark matter, that mysterious component of the universe that we cannot see. And microlenses, although small, have the potential to change our understanding of the formation of distant planetary systems. But how do all these lenses relate to cosmology? Gravitational lenses are powerful tools that astronomers use to explore the universe. They help us measure the expansion of the cosmos, study dark matter, and understand the evolution of galaxies. Every time we observe a gravitational lens, we are taking a snapshot of the history of the universe, a story that has been unfolding for billions of years. Imagine you are a detective of the universe, searching for clues in every corner of the cosmos. Gravitational lenses are like the footprints that guide you in this mystery. With each discovery, we get a little closer to answering fundamental questions about our place in the universe. What lies beyond what we see? How did everything we know come to be? As we advance in our understanding of gravitational lenses, we also realize that they are a reminder of how small we are in the vast ocean of the cosmos. Every time we look at the sky, we are looking back in time at events that occurred billions of years ago. Gravitational lenses connect us to that history, showing us not only what is there, but also what has been. With the advancement of technology, astronomers are discovering more about these lenses and the secrets they hold. New telescopes and observation techniques are revolutionizing our understanding. Gravitational lenses are the pathway to new frontiers in astrophysics and cosmology, inviting us to continue exploring and questioning. So as we reflect on these fascinating phenomena, let us remember that each type of gravitational lens has its own role in the cosmic theatre. Together, they offer us a clearer view of the complexity of the universe. Who knows what other secrets they will reveal to us in the future? The search continues, and each discovery brings us one step closer to understanding the mystery of our existence in this vast and wonderful cosmos. Cosmic mirages are one of the most fascinating phenomena that the universe offers us. Have you ever imagined how it is possible for us to see distorted images of distant galaxies? This happens thanks to a phenomenon known as gravitational lensing. The light from distant objects can be bent by the gravity of a massive object that stands in its path, creating spectacular images that astonish and often confuse us. When we observe the sky, we do so with the hope of finding answers to fundamental questions about our place in the universe. But what happens when the light of those answers is distorted? Einstein's arcs and rings are visual examples of what occurs when the light from a distant galaxy passes near a cluster of galaxies that acts as a lens. Imagine that light is like a straight path and gravity is like a hill in the middle of that path. The light bends around the hill, and what we see is an altered image of what is on the other side. The beauty of this phenomenon lies not only in its aesthetics, but also in the information it provides us. Einstein's arcs and rings are not mere visual curiosities. They are powerful tools in the exploration of the cosmos. How is it possible that something as simple as light can reveal secrets about the universe? The answer lies in the way light interacts with matter. When astronomers observe these distortions, they can analyze the mass of the object acting as a lens and better understand the distribution of matter in the universe. But what are the necessary conditions for a cosmic mirage to form? Perfect alignment is crucial. For light to bend significantly, the massive object, such as a galaxy cluster, must be almost perfectly aligned between us and the distant object we are observing. This is like having 3 points in a line: the distant object, the lens, and the observer. If they align properly, the magic happens. What does it feel like to discover a cosmic mirage? For astronomers and astrophysicists, each discovery is a moment of wonder. By observing these phenomena, they can gather data about the mass of galaxy clusters and in turn infer the existence of dark matter, that mysterious substance we cannot see but know is there. In a way, gravitational lenses are like cosmic detectives, revealing clues about the composition of the universe. Cosmic mirages also invite us to reflect on our own perception of reality. Just as light can be distorted by gravity, our perceptions can be influenced by our experiences and beliefs. Gravitational lenses remind us that what we see is not always the complete reality. This phenomenon challenges us to look beyond the superficial and question what we think we know. An interesting aspect of cosmic mirages is that they are not just distorted images. They can appear in different forms, from subtle arcs to complete rings surrounding their central object. Each of these patterns has a story to tell, and each offers astronomers valuable data to understand the structure of the universe. The diversity of these phenomena is a testament to the complexity of gravity and its influence on the cosmos. The ability of astronomers to study these mirages has been greatly facilitated by technological advances. With more powerful telescopes and more sophisticated data analysis techniques, we are now able to detect gravitational lenses that previously went unnoticed. This has opened a new chapter in our quest for knowledge and understanding of the universe. At its core, cosmic mirages are a reminder that the universe is a place full of surprises. They show us that even in the vastness of space, there are ways to understand what seems unreachable. Through the observation of these phenomena, scientists are unraveling the complexities of dark matter and the structure of the cosmos. As we navigate the universe, each mirage we discover offers us a new perspective. It invites us to question, to investigate, and to marvel at the immensity of the unknown. Thus, Einstein's arcs and rings are not just a visual spectacle, but a window into understanding what surrounds us. As we continue to explore the cosmos, the importance of cosmic mirages in cosmology becomes increasingly clear. Each distorted image we manage to capture is another step toward understanding the nature of the universe. It reminds us that, although reality may sometimes be distorted, the pursuit of knowledge and curiosity are powerful forces that will guide us through the darkness of space. What makes astronomers feel like true detectives of the cosmos? Their ability to observe and study phenomena that are beyond human sight. One of the most fascinating methods they use is gravitational lensing. But how does this process work exactly, and what tools do they employ to do it? First, it is important to understand that gravitational lenses act like a huge magnifying glass in the sky, allowing astronomers to see objects that would otherwise remain hidden. Imagine looking through a magnifying glass. Everything becomes clearer and sharper. This is how large, massive objects like galaxies and galaxy clusters behave in space, distorting the light from objects behind them. But how can we detect these subtle effects? Astronomers use a combination of advanced telescopes and specialized software to track the light that has been bent by these cosmic giants. Have you ever wondered how scientists can measure the distance to a star that is millions of light years away? They use gravitational lensing to their advantage, analyzing how light is distorted and amplified to calculate the distance and mass of the objects acting as lenses. There is a very intriguing aspect of gravitational lensing observation. Time. The light traveling from a distant object can take billions of years to reach us. However, when that light curves around a massive object, we may see a flash of light from an object that is in the past. This not only provides information about the structure of the universe, but also allows us to observe the history of the universe in real time. The telescopes used for this type of observation are true marvels of modern technology. Space telescopes like Hubble have been fundamental in discovering and studying gravitational lenses. But what about the telescopes on Earth? They also play a crucial role. These telescopes can observe the sky in different wavelengths, from visible light to infrared and beyond. This allows them to capture different aspects of the objects under the influence of gravitational lensing. Imagine you are in a movie theater watching a film projected on a huge screen. However, instead of seeing a single movie, what you see are several distorted images of the same scene thanks to the lens in the way. This is the effect that astronomers observe when looking through a gravitational lens. They see multiple images of the same galaxy, each distorted differently. But why is this so useful? Because each image can contain different information about the original galaxy, allowing scientists to create a clearer map of its structure and formation. In addition to telescopes, astronomers also use sophisticated software to analyze the collected data. These programs are like detectives searching for clues in a cosmic mystery. They can model how light curves and distorts, and with that, estimate the mass of the object acting as a lens. But how do they know if their calculations are correct? This is where comparison with other observation and analysis methods comes in, creating a robust validation system. International collaboration is also essential in the observation of gravitational lenses. Scientists from around the world share data and discoveries, creating a network of knowledge that benefits the entire astronomical community. This allows for simultaneous observations in different parts of the world, increasing the chances of discovering new phenomena. One of the most intriguing questions astronomers ask is, what else can gravitational lenses tell us about the structure of the universe? The answer is that these lenses offer clues about dark matter and dark energy, two of the greatest mysteries of the cosmos. By observing how light curves, they can infer the presence of matter that we cannot see directly. Finally, we cannot forget that gravitational lenses are not only a tool for studying distant objects, but also help us better understand the history of the universe. Each observation is like a piece of a cosmic puzzle that, when put together, offers us a clearer view of how our universe has formed and evolved over billions of years. The observation of gravitational lenses is a constantly evolving field full of exciting discoveries and surprises. Each new galaxy observed through this cosmic telescope reminds us of how vast and mysterious our universe is. What secrets will gravitational lenses reveal to us in the future? Only time will tell. But one thing is for sure, the search for answers will never stop. Gravitational lenses are much more than a visual phenomenon. They are powerful tools in cosmology that allow us to explore the mysteries of the universe. How can these optical effects shed light on the structure of the cosmos? To understand this, we must first consider how matter is distributed in the universe. Most of us imagine the universe as a vast empty space, but in reality, it is filled with matter, and not just the matter we can see. Dark matter, for example, is an essential component, albeit invisible, that influences gravity and therefore the formation of cosmic structures. When we observe the sky, what we see are galaxies, stars, and other celestial bodies, but behind those images lies a complex web of matter interacting in surprising ways. Did you know that gravitational lenses can act as a map of this invisible matter? When a massive object, such as a galaxy or a cluster of galaxies, lies between us and a more distant light source, its gravity can distort and amplify the light coming from that source. This not only allows us to see the light from objects that would otherwise be hidden, but it also gives us clues about the amount and distribution of dark matter in the universe. It is fascinating to think that by observing these effects, we can deduce the existence of invisible structures. Gravitational lenses are not just an isolated phenomenon, they are a mirror reflecting the history of the universe. When an astronomer detects a gravitational lens, they are capturing a moment in time, a distorted image that reveals the influence of gravity on space-time. But how does this translate into a deeper understanding of cosmology? Gravitational lenses allow us to study the distribution of dark matter in galaxy clusters. Why is this so important? Dark matter makes up about 85% of the universe's mass, and without it, we could not explain how galaxies cluster and move. As astronomers analyze the patterns of light distortion, they can infer the amount of dark matter present in those clusters. This information is crucial for answering questions about the formation of the universe and its evolution. Imagine trying to piece together a puzzle, but many pieces are missing. Gravitational lenses are like those pieces that help you complete the picture. As scientists gather data on multiple gravitational lenses, they can construct a clearer map of how matter is distributed in the universe. Isn't it incredible to think that an optical phenomenon can help us understand something as fundamental as the composition of the cosmos? Moreover, gravitational lenses not only inform us about dark matter, but they also provide insights into how gravity behaves on enormous scales. Einstein's general relativity tells us that gravity is not just a force, but a curvature in space-time. Gravitational lenses are a visual manifestation of this curvature. When we observe how light curves around a massive object, we are witnessing Einstein's theory in action. The observation of gravitational lenses is also interconnected with the expansion of the universe. By analyzing how light is distorted in different contexts, scientists can calculate the rate of the universe's expansion. This has profound implications for our understanding of the ultimate fate of the cosmos. Will it expand forever, or will it eventually collapse? Gravitational lenses can help us answer these questions. Some astronomers have begun to use gravitational lenses as a tool to measure the Hubble constant, which is essential for understanding the rate at which the universe is expanding. By observing multiple lenses in different parts of the sky, researchers can obtain a more accurate estimate of this constant. This is vital for creating a coherent model of the universe and its evolution. Gravitational lenses have become a rapidly growing field of study. Each new discovery offers more clues about the nature of the cosmos, but what about the future? With advanced telescopes such as the James Webb Space Telescope, scientists hope to uncover even more about how gravitational lenses can reveal hidden secrets of the universe. Each new observation promises to open new doors and challenge our current understanding. The relationship between gravitational lenses and dark matter is just one aspect of their potential. We can also use these lenses as tools to explore the formation and evolution of galaxies. By observing how the light from distant galaxies is distorted as it passes near massive clusters, we can learn about the history of those galaxies and how they have clustered over time. In summary, gravitational lenses are a testament to the beauty and complexity of the universe. They allow us to see beyond the visible and understand the structure and composition of the cosmos in ways we never imagined. As we continue to explore these fascinating phenomena, each answer brings new questions. driving us to keep probing the mysteries that surround us. Thus, gravitational lenses become a bridge between what we see and what we have yet to discover in the vast and enigmatic universe. What do a cluster of galaxies and a pair of magnifying glasses have in common? At first glance, it seems like nothing, but in the vast universe, these two elements can have a surprising impact on what we see and understand. Let's talk about Abell 2218, one of the most fascinating galaxy clusters that offers us a unique visual spectacle thanks to gravitational lenses. Imagine you are in a theater, and instead of a movie, you are watching a representation of the cosmos. Suddenly, a group of actors, which in this case are galaxies, gathers on stage, creating a kind of backdrop. This backdrop is not only impressive for its size, but also has a special power. It acts as a lens that distorts the light from objects behind it. This is how Abell 2218 works, a true master of cosmic optics. When observing this cluster, astronomers have noticed something extraordinary. The light from galaxies that are much farther away bends and distorts as it passes near Abell 2218. But what is the result of this phenomenon? The answer is a visual spectacle that leaves scientists and astronomy enthusiasts in awe. Bright arcs and rings that seem to dance around the cluster. These visual effects are known as Einstein arcs and are a testament to how gravity can alter our perception of the universe. What does this tell us about the structure of the universe? Abell 2218 is not just a cluster of galaxies, it is a window into the past. The galaxies we see through its lenses may be billions of light years away, meaning we are looking back in time. Each arc and each ring we see is an image of a universe that existed eons ago. It's as if we have a time machine that allows us to see what the cosmos was like in its youth. Astronomers are not only amazed by the beauty of these phenomena, they also use gravitational lenses to measure the mass of galaxy clusters. But how is this done? Through the distortion of light, they can calculate how much mass is needed to achieve that visual effect. Thus, Abell 2218 becomes a cosmic laboratory that helps us understand the distribution of matter in the universe. However, it is not all that simple. Each gravitational lens is unique, and sometimes the effects can be difficult to interpret. Imagine trying to see through a fogged-up glass. The information can be confusing. Astronomers must be detectives, deciphering the clues that gravitational lenses offer them. Each observation reveals new secrets about the nature of dark matter and the structure of the cosmos. One fascinating aspect of Abell 2218 is that it not only acts as a lens, but is also an extremely massive cluster. This means that its gravity is so intense that it affects other galaxies around it. Scientists have discovered that the interaction between visible matter and dark matter in this cluster is an area of study that is constantly evolving. What secrets does it still hold for us? The Abell 2218 cluster is just one of many examples of how gravitational lenses are helping us unravel the mysteries of the universe. Other clusters have also shown similar effects, and each brings its own unique story and data. Each new discovery brings us closer to understanding how the universe was formed and what its ultimate fate may be. In the search for answers, astronomers have developed new technologies and observation methods. Advanced telescopes and data analysis techniques have allowed scientists to study these gravitational lenses more effectively. But what will happen in the future? As technology advances, it is likely that we will discover even more clusters and lenses that will offer us even deeper glimpses into our cosmos. The story of Abell 2218 and other gravitational lenses is not just a story of scientific discovery, it is also a story of human curiosity. Since time immemorial, we have looked at the sky in wonder and with questions. Today, thanks to modern physics and gravitational lenses, we are closer than ever to understanding the vast and complex web that makes up our universe. So the next time you look at the starry sky, think about the secrets that lie behind each star and each galaxy. What are we really seeing? How many stories are waiting to be told? Science through gravitational lenses allows us to be both observers and participants in this incredible cosmic adventure. Dark matter is one of the great mysteries of the universe. Although we cannot see it directly, we know it is there because its gravity affects the things we can observe. But how do we know this invisible matter exists? Gravitational lenses are one of the keys to unraveling this enigma. Through them, scientists have begun to piece together the cosmic puzzle. Imagine you are a detective in a world where most clues are invisible. You have to rely on what you can see to deduce what you cannot. This is how astronomers studying dark matter work. They use gravitational lenses, which are like cosmic mirrors, to glimpse the presence of this elusive matter. When a massive galaxy acts as a lens, it distorts the light from a galaxy behind it. This distortion not only shows us what is happening in space, but also gives us hints about the matter we cannot see. What does the way light curves tell us? The answer lies in how gravity works on a cosmic level. Einstein's general theory of relativity teaches us that gravity is not just a force, but the result of the curvature of space-time. When the light from a distant galaxy passes near a massive object, its path bends. This phenomenon becomes a powerful tool for astronomers. By analyzing how light is distorted, they can estimate the amount and distribution of dark matter in the universe. A fascinating phenomenon occurs when two galaxies align perfectly from our perspective. In these cases, the light from the background galaxy can form a perfect ring around the galaxy, acting as a lens. This ring, known as the Einstein ring, is like a portrait of the effects of gravity on light. But what implications does this have for dark matter? The answer lies in the fact that the amount of distorted light can indicate how much dark matter is present in the galaxy, acting as a lens. Through gravitational lenses, scientists have been able to map regions of the universe where dark matter is denser. These observations have revealed a network of filaments and structures that form the skeleton of the universe. But why is this important? Knowing the distribution of dark matter helps us understand how galaxies formed and how they evolve over time. One of the most intriguing questions is, what exactly is dark matter? Although we do not know its exact composition, there are theories suggesting it could be made up of subatomic particles that interact very weakly with normal matter. Gravitational lenses allow us to make inferences about these particles by observing how they behave in the presence of gravity. The study of gravitational lenses has also led to surprising discoveries about the nature of the universe. For example, we have learned that dark matter is not distributed uniformly. In some areas, there is a higher concentration of this dark matter, which affects galaxy formation. But how does this relate to the expansion of the universe? Dark matter and dark energy are key factors influencing how our cosmos is expanding. Astronomers have used gravitational lenses not only to study dark matter, but also to explore how gravity behaves on cosmological scales. By observing how galaxies act as lenses, scientists can test the predictions of general relativity in extreme situations, which in turn provides a broader context about the nature of space and time. A famous case is the galaxy cluster Abell 2218. This cluster has been studied for years and has provided valuable clues about dark matter. Images of this cluster show multiple arcs and rings of light, which are witnesses to the gravitational interactions at play. Analyzing these patterns allows researchers to estimate the mass of the cluster and therefore the amount of dark matter present. However, the search for dark matter does not stop here. New technologies and telescopes are being developed, promising deeper observation of gravitational lenses and the effects they produce. With each advance, we are closer to understanding not only dark matter, but also the role it plays in the history of the universe. The relationship between gravitational lenses and dark matter is a perfect example of how the invisible can influence the visible. This field of study invites us to look beyond what our eyes can see and to question what we really know about the nature of the cosmos. Dark matter may be a mystery, but gravitational lenses are our compass in this quest for knowledge. Finally, dark matter and its study through gravitational lenses remind us that the universe is a much more complex place than we imagine. Each discovery opens new questions and leads us to a deeper understanding of reality. As we continue to explore the cosmos, gravitational lenses will remain a beacon of hope in our search to understand the nature of the universe and our place in it. Gravitational lenses are a fascinating phenomenon that not only allow us to observe the universe but also provide clues about its expansion. How is it possible for a massive object to influence the light passing around it? The answer lies in the way the gravity of a massive object, such as a galaxy or a cluster of galaxies, can curve space-time. This behavior is one of the most surprising predictions of Einstein's general theory of relativity, and its study provides us with a unique window into the nature of the universe. When we talk about the expansion of the universe, we refer to the idea that the cosmos is constantly growing, pushing galaxies away from each other. But how can we measure this expansion? This is where gravitational lenses come into play. Imagine that the light from a distant galaxy travels through space and encounters a cluster of galaxies on its way. The gravity of this cluster acts like a lens, distorting the light and allowing us to see that distant galaxy in a way that would be impossible without that lens. Astronomers have developed ingenious methods to measure the amount of curvature that light experiences as it passes near these massive objects. This curvature not only helps us observe galaxies that would otherwise be hidden, but it also allows us to gather information about the matter that makes up those clusters. But why is it so important to know the amount of expansion of the universe? The answer is that it helps us understand the history of the cosmos from its birth to its future. By studying gravitational lenses, scientists can determine how matter is distributed in the universe. This includes both visible matter, such as stars and galaxies, and dark matter, which we cannot see directly. Dark matter is essential for understanding gravity in the universe. Without it, our observations of the expansion of the universe would not make sense. Gravitational lenses act as a map that guides us through this invisible matter. Imagine you are trying to navigate a maze. If you had a map that shows you where the walls are and which paths are blocked, you could find the exit much more easily. Gravitational lenses are that map in the vast maze of the universe. They allow us to see where dark matter is and how it affects the expansion of the cosmos. In this sense, gravitational lenses not only act as tools for observing the past, but also help us foresee the future of the universe. With each new observation, astronomers collect data that allows them to refine their expansion models and make more accurate predictions about how the universe will behave in the coming billions of years. What does the future hold for us? That is one of the most intriguing questions we can explore through cosmology. An interesting aspect is that gravitational lenses can reveal discrepancies in our theories. If we observe that the light from distant galaxies is distorted in an unexpected way, this could indicate that there is something in our understanding of gravity and expansion that we need to reevaluate. Each discovery, each new piece of data, is like a piece of a cosmic puzzle that we are trying to solve. The relationship between gravitational lenses and the expansion of the universe also leads us to reflect on the role of dark energy. This mysterious form of energy seems to be driving the acceleration of the universe's expansion. Gravitational lenses, by allowing us to study the distribution of matter, help us better understand how this dark energy interacts with gravity. Looking ahead, the use of cutting-edge telescopes, such as the James Webb Space Telescope, promises to revolutionize our understanding of gravitational lenses and the expansion of the universe. These telescopes not only have the capability to observe the universe in different wavelengths, but can also capture images with unprecedented clarity. This will allow us to observe weaker and more distant gravitational lenses, opening a new era of discoveries. In summary, gravitational lenses are much more than a visual phenomenon. They are powerful tools that help us unravel the secrets of the universe. As we continue to explore the cosmos, each new lens we discover gives us a clearer view of the structure of the universe, its expansion, and the mysterious dark matter that composes it. With each observation, we get a little closer to answering fundamental questions about our existence and the future of the universe. The study of gravitational lenses is not only redefining our understanding of the cosmos, but also inviting us to marvel at the vastness of the unknown. Gravitational lenses are not only fascinating phenomena of the universe, they are also powerful tools that help us better understand the expansion of the cosmos. How is it possible for such a massive object as a galaxy to influence the light we see from distant objects? To unravel this mystery, we must first explore how these lenses work in the context of the expansion of the universe. When we talk about the expansion of the universe, we refer to the idea that since the Big Bang, galaxies are moving away from each other. This phenomenon was discovered by astronomer Edwin Hubble, who observed that the most distant galaxies are moving faster than those that are closer. But what role do gravitational lenses play in this scenario? Imagine that galaxies are boats on an expanding ocean. As the ocean expands, the boats drift apart. Gravitational lenses are like waves in this ocean that can bend the light from those boats, allowing us to see them in a different way. Gravitational lenses can act as amplifiers of the light from galaxies that would otherwise be too faint to be seen. By doing so, they offer us a clearer view of the most distant galaxies and their movement through space. This is crucial for studying the expansion of the universe, as it allows us to measure the speed at which these galaxies are moving away from us. If we can observe how the light is distorted due to these cosmic mirrors, we can infer valuable information about the rate of expansion. The relationship between gravitational lenses and the Hubble constant, which describes the rate of expansion, is an active area of research. What if I told you that gravitational lenses can help us measure this constant more accurately? When a distant galaxy passes near a massive object such as a galaxy cluster, the light from that galaxy is bent and amplified. By analyzing this light, scientists can calculate distances and speeds with a precision that would not be possible without the help of these lenses. It's like using a telescope that not only amplifies light, but also gives us information about the speed of those boats in the ocean. But are there any limitations to this technique? Like everything in science, there are challenges. Gravitational lenses depend on the precise alignment between the distant galaxy, the massive object, and us as observers. This alignment can be rare, meaning we cannot always rely on them for data. However, when it occurs, they are like a gift from the universe, revealing hidden secrets and helping us build a map of how the cosmos expands. The importance of gravitational lenses in precision cosmology cannot be overstated. They offer us a new way to look not only into the past, but also into the future of the universe. By understanding the rate of expansion, we can formulate theories about the ultimate fate of the cosmos. Are we destined for a future where the universe expands indefinitely, or is there a possibility of a big crunch where everything returns to a point? Gravitational lenses help us get closer to answers. One of the most exciting contributions of gravitational lenses is their ability to reveal the distribution of dark matter. This mysterious component of the universe, which does not emit light and is difficult to detect, can be inferred through the effects of lenses. Isn't it fascinating to think that things we cannot see can influence what we observe? Lenses act as a bridge between the visible and the invisible, helping us understand the structure of the universe on a larger scale. Moreover, gravitational lenses are useful for studying the history of the universe. By observing how the light from distant galaxies bends through different epochs, scientists can gain insights into how the rate of expansion has changed over time. This line of research offers a window into the evolution of the universe, allowing us to see how the forces that govern it have changed over time. As we advance in the study of gravitational lenses, the future looks bright. New telescopes, such as the James Webb Space Telescope, are designed to leverage these techniques, promising to revolutionize our understanding of the cosmos. With each new observation, we get closer to unraveling the mysteries of the universe and of expansion itself. With each discovery, we are reminded of how interconnected all aspects of the universe are. Gravitational lenses are not just an isolated phenomenon, they are a thread in the vast tapestry of cosmology. Every time we observe through a gravitational lens, we are not only seeing distorted light, but also looking into the heart of how the universe works. In essence, gravitational lenses not only enrich our understanding of cosmic expansion, but also invite us to reflect on our place in the cosmos. As we continue to unravel these mysteries, the journey is just beginning. Human curiosity drives us to keep exploring, and gravitational lenses are one of the many tools that will help us unveil the secrets still waiting to be discovered. Black holes are like the rock stars of the universe, mysterious, powerful, and full of intrigue. But did you know that besides their fame for devouring everything that comes close to them, they can also act as enormous gravitational lenses? Their ability to distort the light passing near them is a fascinating phenomenon and offers us a unique window to understand both gravity and the universe itself. When a black hole is in the path of light emitted by a distant object, such as a star or a galaxy, its gravity can curve the space-time around it. This curvature acts like a lens, amplifying and distorting the light we see. The result is a visual spectacle that can manifest as bright rings or arcs. But what does this mean for astronomers? How does it help them unravel the secrets of the cosmos? The ability of black holes to act as gravitational lenses is especially useful in the search for other galaxies and cosmic structures. By observing the distorted light that reaches us, scientists can infer the presence of dark matter. This matter, which does not emit light and is invisible, represents about 85% of the mass of the universe. It's like a cosmic puzzle where each piece we discover helps us better understand the whole. Moreover, black holes offer a unique opportunity to study general relativity in action. When light curves as it passes near a black hole, we can see how gravity affects light and time. This not only validates Einstein's theories, but also opens new questions. What else can we learn from these mysterious objects in the future? Imagine for a moment a lighthouse on the coast. Its light spreads over the ocean, but if we place a large object in the path of the light, its beam will be affected. As it approaches the shore, the light will distort, forming curious patterns. Black holes work similarly. But instead of a lighthouse, we are talking about light traveling billions of years from the depths of the universe. Astronomers have detected several supermassive black holes at the centers of galaxies. By studying how these black holes distort the light from the galaxies behind them, we can learn about the distribution of dark matter and the structure of the universe. But not only that, we can also gain clues about the history of the galaxy itself. Every distortion we see is a story of billions of years of cosmic evolution. Imagine that every time you look up at the sky and see a distant star, you are not just seeing light, but also looking through a cosmic lens. This may sound like science fiction, but it is the reality of modern astronomy. The light we observe may have been distorted in surprising ways by distant black holes, revealing hidden secrets that would otherwise remain in the dark. The visual effects produced by black holes are not just curiosities. They are powerful tools that scientists use to explore the universe. Each distorted image is a new set of data that can be analyzed. Astronomers not only observe but also use mathematical models and simulations to better understand the relationship between the lens and the distant object. This type of analysis is essential for unraveling the mysteries of dark matter and dark energy, two of the most enigmatic components of the cosmos. As telescopes advance in technology, such as the new James Webb Space Telescope, the opportunities to study black holes as gravitational lenses only increase. With each new image, we are getting closer to answering fundamental questions about the universe. What is really at the center of those galaxies? How did those supermassive black holes form? Each answer leads us to new questions, creating an endless cycle of discovery. But what about smaller black holes, those that are not supermassive giants? They can also act as gravitational lenses, although their effects are more subtle. These star-sized black holes can create microlenses, distorting the light from distant objects in a more delicate manner. These phenomena are harder to detect, but equally fascinating. What do they reveal about the nature of black holes and their formation? The connection between black holes and gravitational lenses is not limited to the observation of light. It also extends to fundamental physics. By studying how light behaves around a black hole, scientists can test general relativity under extreme conditions. This could lead us to new theories that merge relativity and quantum mechanics. two pillars of physics that still seem to be at odds in certain aspects, we cannot forget that understanding black holes as gravitational lenses also has implications for our knowledge about the future of the universe. By studying how light is distorted and amplified, scientists can gain valuable insights into the expansion of the universe. Is it accelerating, decelerating, or remaining constant? Gravitational lenses may offer clues that help answer these fundamental questions. In this journey through black holes and their effects as gravitational lenses, we face a universe full of wonders and mysteries. Each discovery leads us to new dimensions of understanding and reminds us of how little we really know. It invites us to keep exploring, to keep questioning, and above all, to keep marveling at the vastness of the cosmos. In the end, black holes are not just objects of study, but also symbols of human curiosity and our relentless quest to understand the universe we inhabit. What if I told you that the future of gravitational lens research is as close to us as advancements in space technology? Science is advancing by leaps and bounds, and modern telescopes are one of the key tools that will allow us to unravel the mysteries of the universe. The question is, what lies behind this revolution in astronomical observation? As technology improves, so do our capabilities to explore the cosmos. Space telescopes, which orbit the Earth, provide us with a clear view of the universe, free from light pollution and atmospheric distortion. But how do these telescopes influence the study of gravitational lenses? The answer lies in their ability to capture light from distant objects that would otherwise be invisible. One of the protagonists in this story is the James Webb Space Telescope, an instrument designed to observe in infrared wavelengths. This is crucial, as many galaxies and cosmic structures emit their light in that range. Can you imagine being able to see beyond what our eyes can capture, revealing hidden secrets of the universe? This is how the James Webb will seek to answer questions that have intrigued astronomers for decades. This telescope has the ability to observe gravitational lenses in action. By capturing light distorted by massive objects, it provides us with a unique perspective on how gravity works on cosmic scales. But what does this mean for our understanding of the universe? Every image captured by Webb is like a puzzle piece that helps us assemble the story of the cosmos. The future is not limited to the James Webb Telescope. There are other projects in development that promise to take the study of gravitational lenses to a new level. One of them is the Euclid Space Observatory from the European Space Agency. This telescope will focus on mapping dark matter and dark energy in the universe, two fundamental components that we still do not fully understand. How does it feel to know that we are on the brink of discovering what makes up most of the cosmos? In addition to these telescopes, astronomers are using innovative techniques, such as artificial intelligence, to analyze large amounts of data obtained from observations. Imagine you have a pile of images and need to find a hidden treasure among them. This is where artificial intelligence becomes an invaluable tool, helping scientists identify gravitational lenses that may have previously gone unnoticed. International collaboration also plays a crucial role. Astronomers from around the world are working together, sharing data and resources to maximize our observational opportunities. This is like a great orchestra where each musician contributes their talent to create a cosmic symphony. Isn't it fascinating to think that while we are here, teams on different continents are joining forces to understand the universe? As we move forward, we must also consider how this research is influencing other areas of science. Gravitational lenses not only teach us about gravity and dark matter, but also offer methods to study the evolution of galaxies. Just as an artist observes their canvas from different angles to capture the essence of their work, scientists use gravitational lenses to see the evolution of cosmic structures over time. The future also holds the possibility of observing rare events, such as galaxy collisions and the effects of supermassive black holes acting as lenses. Each of these events is an opportunity to learn more about how the universe behaves. What secrets will the cosmos reveal to us in the near future? Human curiosity is insatiable, and space exploration is an extension of that endless quest for knowledge. Gravitational lens research impacts our understanding of the expansion of the universe. As scientists measure how lenses affect light, they can gain insights into the rate of cosmic expansion. This is like adjusting the focus of a camera to get the best image. Every little detail counts when it comes to capturing the history of the universe. Finally, it is exciting to think about how this research will inspire future generations. Young scientists and astronomers who look to the sky today and dream of discovering the unknown will be propelled by the advancements being made now. Who knows? Perhaps the next great discovery in astrophysics will come from a young mind inspired by today's telescopes. In conclusion, the future of gravitational lens research is bright and full of possibilities. With emerging technologies and unprecedented global collaboration, we are in a privileged position to unravel the mysteries of the universe. Each new discovery not only expands our knowledge, but also fuels our curiosity and desire to explore the unknown. What will the cosmos hold for us in the coming years? Only time will tell, but one thing is certain: the adventure has just begun. Gravitational lenses are a fascinating phenomenon that not only allow us to see the universe in a different way, but also provide clues about how galaxies formed and evolved over time. The first question that arises is, how can these massive objects, often located billions of light years away, influence the light we see? The answer lies in the way the gravity of these bodies affects the light traveling through space. When we talk about gravitational lenses, we are referring to a kind of cosmic optics. Just as a lens in a camera can focus or distort an image, galaxies and clusters of galaxies act as enormous lenses that can alter the path of light coming from more distant objects. This occurs because, as the light from a distant star or galaxy passes near a massive object, the gravity of that object curves the space around it, causing the light to follow a different trajectory. Interestingly, this phenomenon can create multiple images of the same object, distorting its appearance and creating impressive visual effects. One of the intriguing questions that arise from this phenomenon is, what do these distorted images tell us about the history of the universe? Gravitational lenses allow us to study the distribution of matter in the cosmos, including dark matter, which does not emit light and is invisible to our telescopes. By observing how light is curved and distorted, scientists can deduce the amount and distribution of this dark matter, which makes up most of the universe, in addition to their role in understanding dark matter. Gravitational lenses are also valuable tools for studying the formation and evolution of galaxies. For example, by observing how the light from a distant galaxy is deformed as it passes near a cluster of galaxies. Astronomers can infer how these galaxies have interacted with each other over billions of years. This type of study not only helps us understand how galaxies form, but also how they group and evolve in the vast universe. In this context, another fascinating question arises. What role does gravity play in the formation of large-scale structures in the universe? Gravity, acting as a cosmic glue, gathers matter over time, forming clusters of galaxies and filaments that constitute the cosmic web. Gravitational lenses, by allowing us to observe these interactions, provide a unique window into the processes that have shaped the cosmos as we know it today. As we delve deeper into the study of gravitational lenses, we also encounter the question of how these phenomena can help us measure distances in the universe more accurately. By observing the effect of gravitational lensing, astronomers can determine the distance to the object being distorted. This is essential for understanding the expansion of the universe and the rate at which it is expanding. The relationship between gravitational lenses and the expansion of the universe is particularly intriguing. By studying how lenses affect the light from distant objects, scientists can gain insights into the acceleration of the universe's expansion. Thus, gravitational lenses not only help us see the cosmic past, but also allow us to explore its future. One fascinating aspect of gravitational lenses is their ability to reveal information about black holes. It has been discovered that black holes, like other massive objects, can act as gravitational lenses. This raises the question, what can we learn about the nature of black holes through these phenomena? By observing the gravitational lensing effect around a black hole, scientists can gather clues about its mass and other parameters, thus providing valuable data about these mysterious objects. However, the study of gravitational lenses does not stop at observing individual phenomena. These lenses are also crucial for precision cosmology, where they are used to measure the Hubble constant and other fundamental parameters that describe the evolution of the universe. How are gravitational lenses related to the rate of expansion of the universe? Through methods such as observing distorted objects and analyzing the obtained data, scientists can refine their cosmological models and gain a deeper understanding of the dynamics of the cosmos. As we advance in the research of gravitational lenses, we must also consider the future of this fascinating field. With advanced telescopes like the James Webb Space Telescope, astronomers have the opportunity to explore gravitational lenses further and discover new phenomena. What new mysteries await us in the vast expanse of space? Next-generation technology promises to open new windows to our understanding of the universe and its secrets. Finally, it is essential to reflect on how gravitational lenses have impacted not only our understanding of the cosmos, but also our vision of our place within it. Through the study of these lenses, we have learned that gravity is not just a force that attracts bodies, but also a tool that allows us to explore the universe in ways we never imagined. Thus, gravitational lenses invite us to continue questioning and investigating, reminding us that, in the grand scheme of the cosmos, every answer brings with it new questions. Gravitational lenses are not just a concept in physics, they have found their way into the world of popular culture. From movies to books, these fascinating distortions of light have captured the imagination of many. But how have they been represented, and what do they really mean in the context of stories that explore the cosmos? Let's start with cinema. Science fiction films often play with the idea of intergalactic travel and alternate dimensions. In these tales, gravitational lenses are sometimes depicted as portals to other worlds. Isn't it intriguing to think that, in real life, a massive mass can distort the light from distant objects, creating spectacular images that seem straight out of a fantasy movie? The reality, however, is even more astonishing, as it shows us how gravity can alter our perception of what we see in the universe. A clear example of this can be found in Interstellar, a film that has fascinated millions. The representation of black holes and how they can influence time and space raises questions about the nature of the universe. Although the movie takes certain creative liberties, the idea that massive objects can affect light in surprising ways is rooted in the real science of gravitational lenses. How can we not marvel at the possibility that the gravity of a black hole could act as a cosmic lens, distorting not only light but also our understanding of time? Science fiction books have also contributed to popularizing the concept. Authors like Arthur C. Clarke have explored the idea that advanced civilizations might use gravitational lenses to communicate or travel through the cosmos. Imagine a future where we can manipulate gravity to see beyond the limits of our own universe. That notion evokes a mix of curiosity and wonder. In that sense, gravitational lenses are not just tools for astronomers, they are symbols of what humanity could achieve in its quest for knowledge. On the other hand, video games have also played their part. Titles like Mass Effect and Elite Dangerous feature gravitational lenses as elements within their gameplay. Players must navigate star systems where these lenses can affect their trajectory. This not only adds a level of complexity to the game, but also introduces players to scientific concepts in a fun and accessible way. Who would have thought that learning about physics could be so entertaining? Moreover, these concepts have been used in documentaries and educational programs that aim to inspire the next generation of scientists. By showcasing stunning images of distorted galaxies and arcs of light, they spark the curiosity of viewers. Wouldn't it be amazing if, through these images, more young people became interested in astronomy and physics? The connection between entertainment and education is powerful, and gravitational lenses are an excellent example of how science can captivate audiences. However, not everything is fantasy. Gravitational lenses have also been a topic of discussion in philosophy and ethics. In a world where science can alter our understanding of reality, deep questions arise. What does it really mean to see the universe through these lenses? We face dilemmas about perception and knowledge that have been discussed by philosophers throughout history. Popular culture thus becomes a mirror reflecting our concerns about our place in the cosmos. What about music? Artists have used ideas from relativity and gravitational lenses as metaphors to talk about love, loss, and the search for meaning. The lyrics of some songs reference the distortion of perception, using science as a poetic way to explore human emotions. The connection between art and science is undoubtedly a fertile ground for creativity. When talking about pop culture, it's impossible not to mention television series. In shows like The Expanse, gravitational lenses become a central element of the narrative, showcasing the consequences of gravitational interactions in space travel. In doing so, it provides an opportunity for the audience to learn while enjoying an exciting story. However, there is one aspect that is often overlooked: the role of social media. Platforms like Twitter and Instagram have allowed complex concepts such as gravitational lenses to be discussed and shared in a more accessible way. Memes, infographics, and short videos help demystify science and make it more understandable for everyone. Who would have thought that a simple meme could spark interest in astrophysics? In summary, gravitational lenses have transcended their scientific realm to become a cultural phenomenon. From cinema to video games, these fascinating distortions of light have found their place in our stories and conversations. They invite us to explore not only what the universe is, but also how we understand and represent it in our lives. Science and culture are intertwined, and gravitational lenses are a brilliant reminder of that. So the next time you watch a movie or read a science fiction book, ask yourself, what lessons about the universe and our existence lie behind those stories? In the vast stage of the cosmos, gravitational lenses are a fascinating phenomenon that awakens both curiosity and confusion. Have you ever wondered if they can really distort the light from distant objects? The answer is a resounding yes. However, there are many misconceptions surrounding this concept. Today we will demystify some of the most common myths about gravitational lenses and explore the reality behind these wonders of the universe. One of the most frequent misconceptions is that gravitational lenses are something supernatural, almost like magic. It is understandable to think this way, given that these phenomena seem to blur reality and create images that appear to escape the laws of physics. But in reality, it all relies on the rules of gravity as postulated by Einstein. There is no magic, just a deeper understanding of how the universe works. Gravity, like a great magnet, can attract and bend light, taking it off its straight path and transforming it into something extraordinary. It is often thought that gravitational lenses are something that can only be observed in deep space, far from our everyday understanding. However, in our daily lives, we are surrounded by examples of similar phenomena. For instance, when we look through a glass of water, sometimes the image of an object behind the glass appears distorted. This happens because the water acts as a lens, just as massive galaxies can act in the cosmos, curving the light that passes around them. A common myth is that gravitational lenses only affect extremely massive objects, like black holes or galaxy clusters. While it is true that these objects are the most notable in this context, the reality is that any mass can act as a gravitational lens, as long as it is large enough compared to the objects being observed. So, although gravitational lenses are more impressive in the context of cosmic giants, they are not exclusively limited to them. Another misconception is that gravitational lenses can create images of objects that do not exist. This is not true. What really happens is that the light from a distant object curves around a mass, which can result in multiple images of the same object. But all those images come from a single source. It's like looking through a concave mirror that distorts your reflection, but in reality, you are just seeing your own image from different angles. Some people wonder if gravitational lenses can be used to see beyond what our telescopes can reach. The surprising truth is yes. By studying gravitational lenses, astronomers can observe objects that would otherwise be too distant or faint to be seen. In this sense, gravitational lenses act as a kind of cosmic superlens, expanding our view of the universe and revealing details that would otherwise remain hidden. It is common to hear that gravitational lenses are just a visual phenomenon with no implications beyond aesthetics. But in fact, their study provides valuable information about the distribution of matter in the universe, including dark matter. By analyzing how light curves around these lenses, scientists can infer the amount of matter present, even if we cannot see it directly. This makes gravitational lenses powerful tools for understanding the structure of the cosmos. Another persistent myth is the idea that gravitational lenses are rare and uncommon in the universe. In reality, these lenses are more common than we think. Whenever we observe a galaxy cluster, there is a good chance that we are seeing the effects of gravitational lenses. So, even if we are not always aware of it, we are surrounded by these phenomena in the vast fabric of space. The notion that gravitational lenses affect all objects equally is also misleading. The reality is that the magnitude of the lensing effect depends on the mass of the object acting as a lens and the alignment between the observed object, the lens, and the observer. This alignment is crucial. That's why not all galaxies produce spectacular visual effects. It's like a light lamp casting different shadows depending on the position of the objects in its path. Finally, there is the belief that gravitational lenses are a phenomenon that can be ignored due to their complexity. However, every time we look at the sky, we are seeing the result of large-scale gravitational interactions. Understanding gravitational lenses is not just a scientific curiosity, it is fundamental to deciphering the mysteries of the universe and our own existence within it. In the end, gravitational lenses are much more than simple optical illusions. They are a window into the cosmos, a reminder that reality often surpasses fiction. As we continue to explore and understand these phenomena, we come a little closer to unraveling the secrets of the universe and our own story within it. So, the next time you find yourself marveling at a flash of light in the sky, remember that behind that light there could be a gravitational lens, revealing a world of wonder and mystery. How does the study of gravitational lenses influence our daily lives and the advancement of science and technology? This cosmic phenomenon not only offers us a window into understanding the universe, but has also had a significant impact on various disciplines. Gravitational lenses, by distorting the light from distant objects, have allowed us to discover and understand things that once seemed unattainable, from the nature of dark matter to the expansion of the universe. But how does this translate into advancements that touch our daily lives? Modern physics, driven by discoveries like that of gravitational lenses, has led to remarkable technological innovations. For example, the theory of general relativity, which is the foundation of this phenomenon, has enabled the development of technologies such as GPS. Without the correction of relativistic effects in satellites, our navigation applications would not be accurate. The distance between one point and another on Earth may seem straightforward, but relativity shows that time and space behave in surprising ways. Thus, gravitational lenses are not just an abstract concept. They fuel technologies that we use every day. In the field of astronomy, gravitational lenses have revolutionized the way we observe the universe. Through them, astronomers have been able to detect galaxies that would otherwise have remained hidden in the vast and dark cosmos. This discovery not only enriches our knowledge about the formation and evolution of galaxies, but has also led to the development of new observation and data analysis techniques. Who would have imagined that such a distant phenomenon could have such close repercussions on our understanding of space? The intersection between gravitational lenses and telescope technology is another fascinating example. Modern telescopes such as the Hubble Space Telescope and the James Webb have been designed to take advantage of these natural lenses. By utilizing the magnification they provide, scientists can observe details that were previously invisible. Isn't it amazing to think that light distorted by a distant galaxy can give us clues about the composition of the universe? Delving into the field of particle physics, gravitational lenses also contribute to the search for dark matter. This mysterious component of the universe represents a large part of its mass but does not emit light and cannot be detected directly. By observing how the light from other galaxies curves around it, scientists can infer its existence and properties. This type of research opens new avenues in physics, challenging our preconceived notions about matter and energy. Moreover, the understanding of gravitational lenses has driven the development of imaging technologies in other areas. For example, in medicine, advanced imaging techniques benefit from similar principles. The way light behaves can be applied to improve the resolution of medical images, which in turn can aid in more accurate diagnoses. In this way, the study of the cosmic becomes an invaluable tool in human health. The applications do not stop there. In the field of communication, concepts derived from the study of gravitational lenses have influenced the development of optical communication networks. The way light behaves in different media can parallel how data is transmitted through networks. The lessons learned from the universe can, therefore, be reflected in the development of technologies that connect people in the present. Research on gravitational lenses has also fostered international collaboration. Projects like the European Southern Observatory and the Event Horizon Telescope have united scientists from different countries in a common effort to unravel the secrets of the universe. This collaboration not only enriches science but also promotes a culture of idea and knowledge exchange, which is fundamental for the advancement of any discipline. Isn't it inspiring to think that the study of such a distant phenomenon can unite brilliant minds around the world? The curiosity sparked by the study of gravitational lenses has also influenced scientific education. The fascination with the cosmos has led to an increase in interest in STEM careers. New generations are drawn to science and technology, inspired by discoveries in cosmology. This phenomenon has the potential to cultivate a greater appreciation for scientific research and the importance of understanding our place in the universe. In the realm of philosophy and ethics, gravitational lenses also raise intriguing questions about the future of humanity. As we explore and understand more about the universe, questions arise about our responsibility in preserving our home and in the use of technology. How should we use our knowledge to ensure a sustainable future? Gravitational lenses, by opening our minds to the unknown, also remind us that we must be aware of our actions in the present. Finally, when considering the impact of gravitational lenses, it is essential to recognize that this phenomenon is just one example of how science intertwines with all areas of our lives, from the technology we use daily to the big questions about our existence. Gravitational lenses remind us that every discovery in the cosmos can have repercussions on Earth. Human curiosity, driven by the desire to understand the universe, remains a powerful force that drives the advancement of science and technology. So, what future awaits us as we continue to explore the mysteries of the cosmos? Gravitational lenses are not only a fascinating phenomenon in cosmology, but they also offer us a unique opportunity to reflect on our existence and the vast universe that surrounds us. What do these distortions of light tell us about the nature of reality? In a profound sense, gravitational lenses act as mirrors that reveal hidden truths, not only about distant galaxies, but also about ourselves and our place in the cosmos. When we look at the sky, we do so with curiosity and wonder. The stars, planets, and galaxies seem to be an eternal spectacle, but have you ever stopped to think about the immensity of what lies beyond what we see? Gravitational lenses show us that the universe is full of surprises and that light can be manipulated in ways we could never have imagined. This invites us to question how our perception of reality may be influenced by factors we cannot see. When observing a massive object in space, such as a galaxy, we are not only seeing its light, but also the light of everything behind it. This phenomenon reminds us that the universe is a complex web of interactions. Every star we see, every galaxy we observe, is connected in some way, creating a visual story that unfolds before our eyes. What other invisible connections might be affecting our own lives here on Earth? Gravitational lenses teach us that gravity is more than just a simple force that attracts objects. It is a curvature of space-time that can alter light itself. This concept invites us to reflect on the nature of reality. If light can be bent by gravity, what other things in our daily lives might be influenced by invisible forces? Often our perceptions are shaped by experiences, beliefs and emotions that we cannot always identify. The curiosity about the cosmos also raises questions about time. Gravitational lenses allow us to see the past, as if we had a time machine. When we observe the light from a distant galaxy, we are seeing what it was like billions of years ago. This aspect of the universe reminds us that time is a dimension intertwined with space, and that our actions in the present can have repercussions in a distant future. How are we shaping our own future through our daily decisions? On a more philosophical level, the study of gravitational lenses leads us to question the nature of existence. If the universe is so vast and complex, what does it mean to be human in the midst of all this? The struggle to understand our place in the cosmos can be a source of anxiety, but also of inspiration, just like the light that travels through a gravitational lens. Our lives are filled with unexpected twists and surprises. Could we learn to accept uncertainty as part of our experience? The search for answers to existential questions can also be a lonely journey. However, gravitational lenses teach us that we are not alone. By observing how massive objects influence the light we see, we can remember that we are part of a broader community connected through the fabric of the universe. Science and philosophy can coexist, providing us with tools to explore both the cosmos and our own being. Dark matter, which is revealed through gravitational lenses, is another reminder that there is much in the universe that remains hidden. What other truths have we yet to discover? Science is constantly advancing, and each new revelation pushes us to look beyond what we think we know. This drive toward discovery is a fundamental part of what it means to be human. In popular culture, gravitational lenses have inspired countless stories and narratives. From movies to books, this concept has become a symbol of exploration and adventure. It reminds us that, although the universe may be frightening and unknown, it is also full of possibilities. What stories could we tell if we dared to look beyond the obvious? As we move into the future of scientific research, gravitational lenses will continue to be a crucial tool for unraveling the mysteries of the cosmos. Each new discovery brings us a little closer to understanding not only the universe, but also ourselves. Science advances, but our questions remain, inviting us to explore and seek beyond easy answers. Reflecting on gravitational lenses also leads us to consider our responsibility toward the planet and the universe. If we are aware of our connection to the cosmos, what actions should we take to protect it? Each of our decisions has an impact, and just like the light that curves, our actions can have far-reaching effects. Ultimately, gravitational lenses are more than astronomical phenomena. They are a mirror that reflects our own struggles and aspirations. They remind us that although our existence may seem small compared to the vastness of the universe, each of us has a role to play. Curiosity and the desire to understand are powerful forces that drive us forward. Let us reflect on what we have learned. Gravitational lenses invite us to observe the universe with new eyes, to delve into our questions, and to embrace the complexity of reality. At the end of the day, the journey toward understanding is what truly matters. And in this journey, each of us is both an explorer and a discoverer, navigating the vast waters of the cosmos. What does the universe really tell us through gravitational lenses? As we conclude our exploration, it is crucial to reflect on how these cosmic wonders are not only tools of observation, but also bearers of a profound message about the nature of space and time. Gravitational lenses, although they may seem like distant and complex phenomena, connect us to the very essence of who we are and our place in the vast cosmos. When a massive galaxy stands between us and a distant object, It acts as a filter that distorts and amplifies light, allowing us to see not only stars and galaxies, but also the traces of dark matter and energy that make up our universe. But what do these distortions really reveal to us? They show us that the universe is a dynamic fabric, where gravity is not just a force, but a main actor on the cosmic stage. Gravitational lenses are like mirrors of a deeper reality. They invite us to consider existential questions. What lies beyond what we can see? How much of what we think we know about the universe is truly influenced by forces we do not fully understand? Science, through these lenses, offers us a new way of seeing, a new paradigm that challenges our perceptions. Dark matter, that mysterious substance that makes up a large part of the universe and that we have never seen directly, manifests itself through gravitational lenses. Every time we observe a phenomenon like an Einstein ring, we are witnessing a conversation between light and gravity, a dialogue that speaks to us about the invisible structure that holds the cosmos together. The idea that what we see in the sky is only a fraction of reality leads us to question our perceptions even further. What if the universe is stranger and more beautiful than we can imagine? Science teaches us that curiosity is our best tool, and each discovery about gravitational lenses brings us a little closer to unveiling the secrets of the cosmos. As we advance in our understanding of these lenses, we also face questions about time. Relativity tells us that time and space are malleable, that they can be curved and distorted by gravity. What does this mean for our perception of time? Perhaps gravitational lenses are telling us that time is not a straight line, but a labyrinth full of surprises. It is fascinating to think about how this research not only affects cosmology, but also influences everyday technologies. Understanding gravity and light has led to advancements in fields as diverse as satellite navigation and communication. Science is not just a set of theories, it is a tool that transforms our lives. Gravitational lenses teach us that science and poetry can coexist. Every flash of light that passes through a lens is a story told through time. It reminds us that every star we see has traveled millions of years to reach us, and that in a sense we are all part of that cosmic narrative. Looking to the future, the possibilities are endless. New telescopes and emerging technologies will allow us to see even beyond the limits we once thought insurmountable. Who knows what new discoveries await us? Perhaps some of the most intriguing questions have yet to be asked. Each of us is an explorer in this vast ocean of stars and galaxies, and although our lives are just a whisper in the immensity of time, our questions and curiosities connect us to the universe. Every time we look at the sky, we have the opportunity to be part of something much larger. Perhaps gravitational lenses are a reminder that the universe is a place full of mysteries to discover. They challenge us to keep asking, to continue seeking answers, and in that journey we find not only knowledge but also a sense of wonder and connection. Science is a journey, a path without end. As we learn more about gravitational lenses and the structure of the cosmos, we also confront the reality of our own existence. What does it mean to be human in such a vast and complex universe? Perhaps the answers are not as important as the questions we carry with us. Ultimately, gravitational lenses teach us about humility. They remind us that there are forces beyond our control and that knowledge is only part of the human experience. What matters is our ability to keep exploring, to keep questioning, and to marvel at the beauty of the universe. And so, as we close this chapter on gravitational lenses, it becomes clear that we are not only talking about science, but also about a deep connection with the cosmos. Each discovery, each question, and each answer brings us a little closer to understanding not only the universe, but also ourselves. What other mysteries await us in this immense and fascinating universe? The answer is out there, waiting to be discovered.